These are the notes for the weekend on the first part of section 2.6, which is the first section in our next unit. We'll cover 2.6 to 3.4 for the next test. 2.6 is called related rates, and it's an application of what you were doing from 2.1 to 2.5. It's in a separate section because the problems themselves take a long time, so I couldn't really put it on the chapter 2 test and keep that at a reasonable length. So really what related rates are is they're rates of change of two or more variables, generally almost always with respect to time. These are going to be word problems where things are changing over time. Real life-wise, this is used at just an inordinate amount. It's used like in change of, you can even think of miles per hour in your car. It's rates of change, basically of anything over time. And we're going to be using it first in 2.6, just generally so you can get the process down, but then we're going to go exclusively to word problems. So this is a really good section for seeing where this stuff you've been using in the last few weeks gets used in real life. We only generally in here are going to keep it pretty geometric just because those are the only ones right now you have the ability to get equations for. But in real life, I was actually just watching a TV show the other day that my husband had on, and it was on war aircraft, and they were talking about this fantastic aircraft that got built in the 80s, and it was the fastest propeller-driven jet ever to be created. But then they were also talking about how it never really got to production because even though it went like Mach 4 or something like that, the rate of change really is what they were talking about. The propeller was moving so fast, and its rate of change, or it was probably done in radians per second is what it was probably moving, was so great that it exceeded the speed of sound, and it went into what was called supersonic. And so it was so incredibly loud that they said to have that on an aircraft carrier and to have many of them taking off and landing at the same time, just one of them landing was making the people who were working on the runway ill and nauseous, they said. So it was very interesting because it was all about rates of change. We are going to be doing ours more geometrically, and I'm just going to start off with some situational examples so you can see what I mean. So my first one is that we've got a rock that gets thrown into a pond, and what happens is it creates these concentric circles, which all of you have probably seen when you've thrown something in the water. And we've got stuff changing with respect to time. So as time goes by, actually, in this picture, there's two things changing. We would say the radius of each ripple is changing over time, and we would write that probably like this, dr dt, which would be change in radius with respect to time. Now the ones we've been working on were more generic, dy dx, but keep in mind that x is the independent variable that's changing, and y is your f of x, which is dependent upon x. So that's what we have here. It's just going to be more real world. My radius is changing, and it's dependent upon the independent variable of time. So this right here would be called my rate of change. It'd be the radius with respect to time. Now also changing in this scenario is the area of each concentric circle. And so we probably call that dA dt, which would mean it's the rate of change of the area with respect to time. So you can see how that whole with respect to x from last chapter is coming into play in a real world problem. So the next one, we've got a ladder falling down a wall. So I'm just going to draw a sketch of a ladder here. This is a common one in this section, although it's not very, who really cares about a ladder falling down a wall, but they use this one quite a bit because you know the Pythagorean theorem, which is what gets used with this. So in this situation, the ladder length is what we would call a constant. Over time, it is not changing. And this is going to be important when we set up our word problems, that we're able to identify what's constant in the situation. The ladder length is not a rate of change. It is not changing over time. So we'd say that's a constant. Now we do have two things that are changing. As the ladder slides down the wall, let's call this y and this x. So it says what is changing with respect to time down here on the bottom. And I would say that the distance it is from the wall, which is this x, distance from the wall. And so our rate of change would be dx dt. That is changing over time. And we'd say this is positive because it's moving away or getting greater in length. The other we would say is the height of the ladder on the wall. And I'm just in this situation. You get to pick your own variables. I like when they're set up like this just to call them x and y. Obviously for area I like to call it a. You get to set them up yourself, but choose them wisely. The height on the wall, well, you'd call that dy dt, which is that rate of change as it's falling over time. And again, the ladder will remain constant. We would say that this would actually be a negative rate of change because it's getting, the length is getting shorter. In this way, it's getting longer as that ladder falls. Not too important today, but later it is. So if I were to ask you which one is negative, you'd say dy dt because it is getting smaller over time. So next one up and just the last one, I'm going to say I've got a cylindrical pool. I should probably have put that in there if you want to put it in there. Well, that is leaking water. So let's just go draw a little sketch of that. So here's my above ground pool. It's got a little hole in it, maybe right there, and water's coming out and flooding my lawn. And here's my pool. And when it says what is changing with respect to time, well, again, you've got a picture. The radius isn't changing. The radius of the pool is constant, so I don't have a dr dt on here. But as that leaks, what's happening is the height of this water is going down. So I would say the height of the water is changing with respect to time. And again, I'd probably call that dh dt, which would be the change in height over time. Now again, because that's going down, we're going to have a negative for that when we start doing these problems. We'd also say the volume of the pool is changing over time, and we'd call that dv dt. So here we've got rates of change in real world context. Now before we can start applying these, we're going to start off today just with generic ones. We're going to apply it to the basic XY situation so you can get the process down, and then we'll move into word problems in a little bit. So what I have here is number 1 on page 149. I've got example number 1, y equaling x squared plus 3. So I have y changing with respect to x. And it says x and y are both differentiable functions with respect to time. So what they're saying is that I have two functions changing over time, both y and x. It says I'm supposed to find the rate of change of y with respect to time when x is 1. And then they give me that the change in x with respect to time is 2 at that time. You know, you say, what's going on here? This is really hard to understand in a non-real world context. Again, they start you off with these so you can get the process down. The word problems actually, I think, are easier to understand. But just so we can get the process down, we're going to start with this one. So throughout this section, we're going to use K for what we know and F for what we need to find. All right? So back up on the top up here, if I were to say, well, what do I know in this problem? I know that the change in x with respect to time is 2. And again, because this is a generic problem, maybe it's 2 meters per second or 2 miles per hour, I don't really know. So we're just going to say it's 2. And my goal is to find dy dt when x equals 1. So first thing I'm going to do is differentiate both sides. And again, this will be with respect to time. So the very first thing I'm going to do is I'm going to take dy dt is equal to dx squared plus 3 dt. Basically, I'm taking the derivative of both sides, but I'm doing it with respect to time. So it now says use the chain rule on the given side. And by the given side, I mean this. Notice again, we don't have a match in variables here. It's not dx squared dx. It's dx squared plus 3 dt, which means I've got a chain rule situation going on right here. And again, whenever you have a non-match in variables, x is itself a function. And so I'm going to do the derivative with respect to x. So I'm going to say it's twice x, but then I need to do x with respect to time. And again, it's also plus 3, but the derivative of a constant is always 0 regardless. So I'm going to point at this. I know this, and I know this because they gave it to me. So it says label each part as K or F, and I need to find this. That's optional. You don't have to label them. I just like to do it. So what I've got here is my change in y with respect to time is twice x, which they told me is 1, and they told me my change in x over time, when x is 1, is 2. So my answer is just 4. And so this is I'm not a big fan of these kinds of problems, but they're giving them to you so you can get the process down before we get into the word problems. So it's a nice short little notes. I'm almost done here. I'm going to do this next one. It's number 6 on page 154, if you're wondering. But the original problem was y is equal to 1 over 1 plus x squared. And they tell you the change in x with respect to time is equal to 2. And they tell you to find the change in y with respect to time when x equals -1. And really, I just want you to get the process down. So let's go ahead and start this. The first thing we're going to do is write y in a form which makes it easy to differentiate. So I'm going to rewrite it like that. Its first step in the process is to take the derivative of both sides with respect to time right now. So that would be dy dt is equal to d1 plus x squared to the -1 dt. All I'm doing is taking the derivative of both sides, very much like when we did implicit differentiation. So now I say that my dy dt is equal to, and again, I don't have a variable match here, so I'm going to consider the chain rule. I'm going to take the derivative of the inside function with respect to x, and then I'm going to do x with respect to t. So I would say that's -1 times 1 plus x squared to the -2 times the derivative of the inside, 2x, and then dx dt. It's a chain rule problem where you just kind of tack that on. I'm going to rewrite it a little nicer here in -2x. And then because that's a negative exponent, I'm going to send it to the bottom. So I basically just cleaned up this whole part, made it a little more user-friendly, and that would be dx dt. So this is what dy dt is. And right now, if I were to go label stuff, I know what x is. It says it's -1. I know that. I know what x is. I also know dx dt equals 2. So I know this. So right now, my last step is basically just plugging it in. So I'm not going to take up your time to go plug a, well, I suppose I could. So I do -2 times -1, because it said x is -1, over 1 plus -1 squared, times the change in x over time, which they told me up here, is 2. And you would go clean that up and you would have your answer. Again, the main reason for doing these 1 through 11 is just so you can get the process down. If you look ahead to the problems past number 11, you're going to see they become much more real-world applicable, where y is actually some function representing volume or surface area or speed or something like that, and it's changing over time, and this is really going to mean something. But for now, we're just going to practice getting the process down. So it's 1 through 11 odd, and number 11 is kind of tricky, so I'm going to post that one if you get stuck on it. This will be due on Monday, 1 through 11 odd. If you need help, check on CalcChat, and I will put number 11 up there because I think it deserves a little time. So that's it for this.